Hello, and I'm back on YouTube, having not been on or doing any videos for some time because there's been nothing worth doing. And today I'm going to look at this little board I bought, which is a wideband RF amplifier. As you can see, it's written on there, 0.1 to 2000 megahertz, 100 kilohertz up to 2000 megahertz. The gain of 30 dB, or roughly 9 to 12 volts. Very cheap, as most of these things are, made in China. And I'll just show you what it looks like on the eBay. It's a bit of an angle, but you get the general idea. £7.39. So, not a lot of money, and amazing what they can do. And it has a tiny little chip in there, which is almost certainly an MMIC, monolithic microwave integrated circuit. I've come across those many times before, mainly the ones that were made by Avantec or HP or mini circuits. Very nice little 50 ohm input, 50 ohm output devices with variable amounts of gain and power outputs. The reason I wanted to try one of these is because of this project I've been asked to do. I know this radio amateur in Swindon who I did a few repairs for last year. He's got an LED sign which is on air, and at the moment he has to just turn it on and off manually. Well, what he wanted was for some device that would pick up his signal when he transmitted anywhere from HF up to 2 meters, probably, maybe even 70 centimeters, would pick up his signal and turn the sign on. So the RF's got to be picked up, amplified, then it's got to trigger the sign. So this is what I'm roughly proposing to do to achieve that. Whether I will or not is another matter. So I have a short aerial antenna plugged into this little board, and then that's detected, amplified by 30 dB, because it will be relatively weak on a short antenna. And remember, it's got to work all the way from HF to 2 meters. It's probably going to get a stronger signal on 2 meters than it will on HF. And he's limited in power to 25 watts. So it's not going to be enormously strong. And after the amplifier, if there's enough signal there, it will be detected by a Schottky diode, a bit like a field strength meter. This is only a basic layout. It's going to be more complicated than this. There'll be usually another diode down to earth, and a blocking capacitor and whatever. There's already one of those on the board. And then once it's become detected and produced a DC signal, which is smoothed with a capacitor, they'll have to go into a DC amplifier of some sort, and let's put an NPN here. This is probably not the right way around to doing this, because that point's going to go low when it senses a signal. And anyway, once it produced a signal, it is designed to drive, might have to use a PMP there, I don't know, drive a MOSFET configured as if it's an N channel, you have an open drain, and then one end of the sign connects to the positive supply, which is 12 volt, and the other end connects to the drain on the MOSFET, which will go low. If I can sort this nonsense out, it will go low when it detects he's transmitting, turning the sign on. The only drawback is that with single sideband, it'll be flashing on and off all the time. So in order to get around that, I'll need a bit of delay on the MOSFET turning off. So some sort of capacitor on the gate, because that's a high impedance anyway at that point. So something else, a capacitor will have to charge up to keep the MOSFET on for half a second or a second or whatever. And that's basically how I think it will work. Whether it will is another matter, probably won't, but at least I'm going to try and do it. Anyway, apart from that, anything else, it'd be nice to play with this little board and see how it works. So, if we look at this board, it's one thing immediately upsets me enormously. To start with, I don't like SMAs, but everything's got SMAs on it. They may have to come off eventually, but for testing I'll leave them on. But if you can see there, the left hand socket is RF output. That causes me much distress. I like my inputs on the left and my outputs on the right, and the right hand socket is RF input. Never mind, we'll get around that one. We can turn it upside down, can't we? That might make me a bit happier, except I can't read what it says anymore, but I don't need to read it. I can read upside down anyway, just about. So what I'm going to do now is I'm going to connect it up to the spectrum analyzer and tracking generator and see if it does what it's supposed to do. And I'm not in the workshop because it's too cold in there, so I brought my old power supply out, which is the smallest and easiest one to carry. It's the first power supply I ever had 40 something years ago from Tandy's Radio Shack. But it's good enough to do what I need to do today. So I need to configure the spectrum analyzer to do what I want it to do, which is go from roughly 0 megahertz, 0 hertz, up to 2 gigahertz. So I'll just do that. So what I'm doing, I'm outputting a signal here, which is going to a through connector, then back into the input socket on the spectrum analyzer. Tracking generator output set to minus 20. Well, it should be set to minus 20. Where's my tracking generator? No, turn that down to minus 20. Because this has got such a high gain, I don't want to put too much signal into it. But now we've got minus 20. And of course we haven't got a very flat display, and we've also got quite a long cable on the input to the spectrum analyzer, which is going to be fairly lossy at 2 gigahertz. But I haven't got many of these with SMAs on them, 2 N types, and I was lucky to find those two. But now what I need to do before I can measure the amplifier is go into there, normalise the display, and that eliminates all the losses and everything, so you get a flat line basically of 0 dB, so I can measure losses or gains. And it's a bit noisy, but it's because I've got such a wide frequency range I'm measuring over, and I've also got 40 dBs of attenuation, which is rather a lot. I don't think I need to. That's 30, 20. Okay, so time to connect up this little board, and I think I've got the power supply set to about 12 volts. So can't measure the current at the moment, but I measured it on my other power supply and it was about 30 milliamps. Let's unscrew one of these, both of these, plug the board in. So that's the tracking generator. So that goes into the socket on the wrong side. And that's the output signal. Okay, spectrum analyzer is complaining. I'll have to add some attenuation. Okay, 30 dBs of attenuation. Marker. So, now we see the response of this little amplifier. And let me just check my voltage on the decent meter, because the meter on the front panel is fairly hopeless on the power supply. "13 volts, I'll do. Now, as we can see, at 215 megahertz we're getting 31 dB of amplification. And I do peak gain is at 1.3 gigahertz at 32 dB. So it's doing more than good enough, considering they specified 30. It's a bit wiggly in its response, but I'm not too bothered about that. It doesn't have to work all the way up to 2 gigahertz anyway. What's this gain at 2 gigahertz? 28. Fine. What about 1 megahertz? Well, it doesn't go down 100 kilohertz, does it? But I don't care about that either. I mean, by 5 megahertz it's up to 31 dB. Obviously, the radio amateur bands don't start till 1.8. I don't think he uses 1.8 anyway. And I think he's more interested in 10 meters than anything else. But as we can see, it's well over 30 dB all the way across. So what else do I want to do with it in measuring it? We can measure its maximum output power, because I've no idea what that is. Don't think it said in the eBay listing. So if I turn off normalizing and right, now I know what I'm doing. So at the moment, with minus 20, I'm getting nearly 10 dB output at 700 and something megahertz. Move it down a bit because it's not needed to go that high. But anyway, 10 dB output. So if I increase the tracking generator level, I know what those spikes are. Well, I'm not going to worry about that. Mm. 12 dBm, and let's see if I can make it compress. Well, if I stick 0 dBm into it, then it kind of compresses and doesn't amplify anymore, which is understandable. In fact, it starts about -3. So yeah, 13 dBm is about the most you can get out of this little board. Dropping off a bit towards towards 2 gigahertz, but we're not interested in that high anyway. And the peak power is nearly 14 dBm, which is quite a bit, really. Quite a bit, and it is actually getting a little bit warm. Now my wire's fallen off. There we are. So, what does 13 dBm equate to in voltage? I looked it up yesterday. I think it's about a volt into 50 ohms. Might not be that high. Can't remember. I can't convert from dBm to volts that easily. I have to look it up. But that's into 50 ohms. The output will effectively be into an open circuit, well, to a diode anyway. It won't be an open circuit, but it won't be a 50 ohm load on it. So I think that'll be quite an interesting little board to play with. It may or may not do what I want it to do, but if it doesn't, it may have other uses in the future. So I think that's about it, really. Not a very exciting video, but there may be more to come as I progress with this project, but at the moment it's too cold to go in my outside workshop, but it will get warmer probably next week, so then I'll do a bit more on it. Anyway, that's about it for now. Thanks for watching. Bye for now.